This is example 4-2, the mixing tank. So as you can see, we have two different fluids coming in. We have glycerin and oil both flowing into this tank, and they're mixed in this tank, and then they flow back out at the bottom. And we are asked to determine the average density at which the mixture flows out of pipe C. We know what's coming in, so how do we know what's going out? Well, to do that, we'll start out with drawing ourselves a control volume. All right, so we know the volume isn't changing, so it's going to be a fixed control volume. And if we kind of do a cross section through it, right, we can say we have something that looks a little bit like this. Something like this, right? These obviously don't have to look perfect. So these would be our control volume. Now we also know once we have a control volume, we need to figure out where the inflow and outflow surfaces are. Remember, surfaces are always outward positive. So we can say this would be A. This would be a B, and then going out would be a C, right? Always perpendicular to the surface and pointing outwards. And then we also have some velocities. No, the velocities are going positive down in this case. So that would be VA. This would be VB. And then this one would be VC. All right, so now we have all our different control volumes and control surfaces. So we can note that this is a fixed control volume. We have steady flow, right? The velocities don't change over time. We have incompressible flow. And we're going to use average velocities because we're not giving any information. All right, so with that, we can go and look at our equation here, our continuity equation, right? So the original version of this would be, that should be a partial d dt over the control volume of rho times dv plus integral over the control surface of rho times v times dA equal to 0. Now we just said that we have incompressible flow or incompressible fluid, right? Which means that our rho is going to be constant, so we can just divide it through and we don't need rho anymore. What else can we say? Well, we can say from a volume standpoint, there's not going to be any change within the control volume, right? The tank is not getting bigger or smaller. There's not a fluid level that's going up and down within the tank. So this is all going to be 0, right? There's no change in the volume. And we can say, well, we're going to use average velocities, right? So we don't have to have this integral here. So what can we say? That means we can say 0 is then equal to is going to be just the outflows and the inflows. So we have to go through. If we look at location A, the velocity and the area vectors are in opposite directions, so it's going to be negative. So we're going to have minus VA times AA. The same is true at B. So minus VB times AB. Now at C, they're both in the same direction, so it's going to be positive. So we're going to have plus VC times AC. All right. So from that, we can figure out what our velocity at C is going to be. So what is our velocity if we solve this for VC? All right, we just have to bring these two over. So we'd be at a positive, so we'd have VA times AA plus VB times AB divided by AC. All right, all these are known, so we can figure out what our volume is, what our velocity is. So VA is given to us. We're not given the area, but we're given the diameter, so we have pi over 4 dA squared plus VB times pi over 4 dB squared. And then at C, it's also pi over 4. Now it's dC squared. Of course, if we have all those pi over 4s, we can just cancel all those out. So we would be left with VA times dA squared plus VB times dB squared divided by dC squared. So if we plug in numbers, then we get 6 meters per second times 0.1 meter squared plus 3 meters per second times 0.08 meters squared divided by 0.12 meters squared, and that gives us 5.5 meters per second. All right, so now we have the velocity going out. Now that we have all those from a volumetric standpoint, we can go in and we can use conservation of mass to make sure we get our outflow density, right? So we can say, let me see, that might see if that fits here. So we can say, now if we take advantage, or if we keep the densities in, right, then we can say, we can just basically add the densities to that equation. So we can say minus VA times AA times the density of oil minus VB times AB times the density of glycerin, and then plus VC, which we just calculated, times AC times, what do we call this one? Let's call it rho out. That's the outflow one. Then we can solve this for rho out. All right, so then basically the same as we have here, just with the densities. So we'd have VA times AA times rho oil plus VB times AB times rho glycerin divided by, now we're left with VC and AC. And I think I'm going to skip the step where we, again show that, if we multiply those, if we write out the areas, right, then we can again cancel out the pi over 4. So I'll just plug in numbers here. Let's write it and then plug in numbers next time. So we get VA times dA squared times rho oil plus VB times dB squared rho glycerin divided by VC times DC. Now if we plug those numbers in, we get 6 meters per second times 0.1 meters squared times 880 kilograms per cubic meter plus 3 meters per second times 0.08 meters squared times 1,260 kilograms per cubic meter, all of this, divided by 0.12 meter squared times 5.5 meters per second. A little squished here, but if we do that, we get 972 kilograms per cubic meters. That would be our density at the outflow. Now, does that make some amount of sense? Yes, because it's between those two values. That's why I think we'll probably have a reasonable answer at the very least.